Happy final Thursday of February. February's already over. I think there's 2 weeks until spring break, too. So we're already just about halfway through the semester. That's exciting. They should have already sent out information on the final.
Yeah, we did.
So that's exciting. We're going to be looking at what's known as a surface of revolution or a solid of revolution. Right, so these types of objects can be obtained by rotating, revolving some curve about some axis, right, or some region about some axis. Right, it's a curve if you're just looking for the surface. It's a region if you're looking for a solid. Now, derivation is in the video. I'm not going to go over the derivation again. And it was derived using the method of cross-sectional slices. Right, we start by looking at the disk method for finding a volume of revolution. So I'm going to find volume of a cone that has height h, whose base has radius r. So what we're doing is we're just deriving a formula from geometry using purely calculus. There are quite a few ways we can get such a cone. If we rotate that region, we'll get a cone, right? We rotate about the y-axis. Rotate that region about the x-axis, we're also going to get a cone. Just be a sideways cone, but a cone nonetheless. For this method, the easiest is to rotate about a horizontal axis. So I'm going to go with rotating about the x-axis. The only thing now is to determine that region. Let's start fresh with what we know. Well, its height is h, right? So I have to extend out to some distance h on the x-axis. It has a radius of r, right? So if you imagine trying to rotate it, this will give r.
Yeah, okay. Sorry, I'm gonna sign on Nick Sin's name. You sign on my name. Nick's. Oh, no, don't worry about it. We're both here though.
Hey. I have to charge you both for the confusion. So I have to be r, right?
Yeah, but we're both here. Yeah, we're fine.
Right, you should now easily imagine this rotates that entire region. We're now going to have cone height h, the base is radius r. How would you represent that line?
R over H. Times X.
So that'd be the length, root r squared plus h squared. The actual line itself would just be r over h times x, right? Since we're going about the x-axis, this method requires the curve be represented as y equals f of x. That's why I'm choosing the x-axis here for disk method. If we were to do it y-axis, we'd have to write this as x equals a function of y, right? Then integrate with respect to y. That's obviously the origin there. Volume by disk method, pi times the integral over your interval, in our case 0 to h. Right, now they call it the radius. Well, the radius is this. It's the distance from the axis of revolution to the end of the region. Well, that's just our function, isn't it? And it's the radius squared. R is a constant, h is a constant. So r over h all squared would be a constant. So let's just factor it out. It'll be a third x cubed as the antiderivative, right? Evaluate that from 0 to h. Get a third pi r squared h. Which is precisely the formula you should have gotten in geometry. So the point of problems like that, where you know the volume already, is to verify the validity of the formula. And obviously, if this wouldn't have given us a third pi r squared h, then the disk method formula is invalid. I believe the video also did a circle. Or, I'm sorry, not circle, a sphere. And it verified that formula. I'm going to look at a cylinder. Right? Specifically, a right circular cylinder. Has radius r. And height h. You take that region and rotate it about the y-axis. You see you get a right circular cylinder. Take that region, rotate it about the x-axis. You also get a right circular cylinder, which just happens to be sideways. But that doesn't matter. It's still going to give us the same volume. Again, disk method. Probably be better just to do y equals f of x. Although it doesn't matter because this is simple anyway. And so we're just going to have to try and describe that region. We want a height h. Well, if you rotate this to form the cylinder, the height would be the distance along the x-axis, right? So let's go like this. Consider that region to say it's 0 to h. Right, that'll now give us height of h. For the radius, that would have to be r there, right? How do you represent that line? This one's simple. It's just y equals r. Pi times the integral 0 to h of our function squared dx. right? That r squared is a constant, so it just factors out. This integral from 0 to h dx is just the length of the interval 0 to h. That length is h. Get a volume of pi r squared h, which again is the formula you have from geometry. So the disk method formula appears to be valid. And in fact, it is. It was derived, so obviously it's true. That's the formula. You have to watch the video for the derivation. I do explain it there. Right, the idea is it comes from the cross sections are disks, and the area of a disk is pi r squared. Except r in this case is the function. Oh, actually, I do a sphere here. Okay. Oh, I did it in the video. It's a volume of a sphere of radius r. Right, we should already know this volume. Getting to stick with rotating about the x-axis. It should be easy to see that if you rotate an upper semicircle of radius r about the x-axis, you get a sphere of radius r, right? Not good enough for government work. What should the interval be on the x-axis? So it goes from what to what? How do you represent that curve? That'd be negative x squared.
Is it the square root of r squared minus x squared?
The square root of r squared minus x squared for an upper semicircle. Because the lower semicircle will be negative square root of r squared minus x squared. Volume pi times the integral from negative r to positive r. Of our function squared. Right. If we look at this as two separate integrals, the r squared dx is just going to be r squared times the length of the interval. What is the length of our interval? That first piece is just going to be 2r cubed. Right, then that second piece is minus a third x cubed, then of course times pi, and then evaluate that minus r to r. Isn't x cubed evaluated minus r to r just 2r cubed? Two pi r cubed minus 2 pi over 3 r cubed. 2 minus 2/3. Yeah, 4/3 pi r cubed, which is the volume of a sphere.
That term.
Here. So r squared, right? If you just integrate r squared, r is a constant, so it factors out. You're left with the integral from minus r to r of dx. That's just the length of the interval. It's 2r, right? So then multiply that by the r squared. That's where the 2r cubed came from. Now, that's just a little shortcut, so you don't have to go. That's x evaluated from minus r to r, which is 2r. If you just recognize that as the length of an interval, it makes it easier to evaluate. So we say here, R is the region bounded, or the region between the x-axis, the curve y equals x cubed, and the line x equals 2. First, we're going to plot this region. We'll then rotate this region about the x-axis and find the volume of the resulting solid. Then we'll rotate it about the y-axis and find the volume of the resulting solid. That's better than what happened in my class last night where it said, take me. Yep. She's never going to live that down. Okay. You can go away, please. And now you're back, of course you are. Okay, what is going on? You. X cubed. It says just the curve X cubed. Right, the region we're looking for between the x-axis, this curve, and x equals 2. Right? So just be region 0, 2, and then up to the curve, right? That makes getting my shaded part easy.
You remember all these names.
How to remember English.
Calculus, but I can't do that and be a person at the same time. Everyone understood.
I just thought the same thing until I had to use it a lot. Trust me, when the difference between getting out of grad school is knowing a coding language and not knowing a coding language, you learn the language real quick. New colors do they have today? Inchworm. Okay. No, it's inchworm color. Had me sold an inchworm. Bless you. That should, uh-oh. I may have to adjust my plot range. See. Yeah, that doesn't go high enough. Bugger. There's our region R, and then of course I can do some apart.
Yep.
Really, you don't give me that option anymore? I'll have to double click to edit. Oh, where's the... Oh. It used to just right click. Assist. I think that's right. Nope. Why does Mathematica update and change everything? I think this is what I want then. Yeah, perfect. Okay. So there is our region. This is what we're going to be rotating. First, about the x-axis. Pi times the integral. 0 to 2, right?
Go back to the question.
We're rotating this region both about the x and the y, and we're going to find the volumes of each region, or each resulting solid. Right, so our radius, again, remember radius is the distance from the axis of revolution to the end of the region, so just to the curve. So just x cubed in this case, right? And then squared. You have to watch the video for the derivation. It has to do with cross sections or disks. And the area is a pi r squared. You should be able to see that this is going to evaluate to 2 to the 7th over 7. And 2 to the 7th is 128. Volume is 128 pi over 7. Now we need to go about the y-axis. That changes things. Because we're now measuring radius from the y-axis to the region. Range I'm going to use for this. Actually, this is the radius that we're really measuring.
That's what that radius. Why is that specific?
The radius of the region. So if you draw a disc, cross-sectional disc, that's the radius of that disc. But again, we have to go. I think I want, yeah, I do want horizontal discs.
But doesn't this make it a washer? Because now there's a second part inside. Unless you want to change it.
Washer is a disc.
Well, it's 2 discs.
The disc can have a hole in it.
Okay.
I don't know why they call it the washer method when it's still just a disc. Discs are allowed to have holes in the middle and still be a disc. Right. Yes, technically what we're doing is what they call the washer method. The washer method breaks down to when you rotate a region between curves, think of it as rotating this region on the volume. Rotate this region, find the volume, and you take the larger volume minus the smaller volume. That gives you the middle volume. That's ultimately what we're doing. That's how the washer method works. We need an interval, excuse me, need an interval for the y-axis. So along the y-axis, what does this region extend from? Now they call it the outer radius minus the inner radius, squareds. The outer radius is just a larger radius, right? That curve is x equals 2. Right, that length is obviously just 2, right? It's from the y-axis to the end. Minus inner radius squared. What is this distance? Cube root of y. dy. Well, that first one is easy. 4 times the length of the interval. Length of 0 to 8 is just 8. Minus add 1 to 2/3. 5/3. 35th pi. Then we have y to the 5/3 from 0 to 8. Which evaluates to 8 to the 5/3. What is 8 to the 5/3?
32.
32. 32 times 3. 96. 32 times 5, 160. And then 160 minus 96 would be 64. This volume is 64 pi over 5. There actually is another way to find that volume, since we're rotating about the y-axis. But we haven't learned that yet.
Which is
Shell method.
L.
Specifically, the method of cylindrical shells.
You also have made like gotten the inverse of that curve and then did stuff about the x-axis.
Theoretically, yes. Right, you're just going to have to adjust the names and stuff. But theoretically, I think it should work. But you have to remember with disk method, when you go to integrate, if you're rotating about a horizontal axis, that's an x-axis, you're integrating with respect to x, so everything needs to be functions of x. If you rotate along a vertical axis, that's a y-axis, then you're integrating with respect to y, which means everything needs to be written as a function of y. Right? It's actually very easy to remember. Rotate about an x-axis with respect to x. Right? So whatever axis you're rotating with respect to, that's what you're integrating with respect to. Looking at the region bounded by the parabola y equals 4x squared, and the lines x equals 0 and y equals 16. It's being rotated about the line y equals -2.
So I think you add 2 to each of those functions, and then it's effectively the same as rotating it around. Actually, wait, but yeah, then it's effectively the same as rotating around the x-axis.
No doubt. This one wasn't too terrible to visualize. Some of them get really bad.
Is that what you're doing? Or
I'm gonna show a plot to make it more clear. And gonna pull the age card. Back in my day, we didn't have, well, actually, we did have Mathematica, but it was way more clunky. And we weren't allowed to use it. We're not allowed to use any calculators. So we had to visualize everything in our head, which was awful. Hated every minute of it. This one actually isn't too terrible to try and visualize, thankfully, but there are some regions that have fun visualizing it. Especially when you move on to Calc 3. Luckily, we have technology to aid us now. So the first thing we're going to do is plot the region. Let's plot 3 for right now. Start by plotting two curves, 4x squared and 16. Actually, do that separately. I don't have to, but I'll do it separately. Huh? What the? Why did it? Go away. Why did you do that? That was weird. Moved the cursor on me for some reason, just as I was executing. So we're being bounded by 4x squared, 16, and x equals 0. What does x equals 0 represent? What is it? Not the origin. The y-axis. Fit in here with our. So we're clearly going 0, but then the question is 0 to what? 2, right? Oh, yes, I forgot to do the plot style. And so there's just the shading of the region. I'm going to define one more thing. Our axis of revolution is y equals -2. I'm going to represent this with a red line. I don't think you let me change color, do you? Oh, yes, you do text color. Perfect. And so that's what we're rotating about. This is clearly a region bounded between curves, right? So they're the two radii, right? Outer and inner. Just write what each line represents. What's the outer radius? How'd you get 36?
16 plus 2, 18. Playing around.
Not the diameter. No. Radius.
Oh, 18.
It's just 18.
I didn't hear radius.
Right. With the graph, it is much more obvious that you add 2 to it. What about the inner radius? Why are you writing it as a function of y?
Oh, so it would just be 4x squared.
It's not just 4x squared. 4x squared would be from the x-axis to the curve. Because remember, this is a horizontal axis of revolution, right? That means it's an x-axis, so we're doing it with respect to x. Because we have to have this distance, right? So 4x squared would be from the x-axis up to the curve. That's the 4x squared, right?
Mhm.
But we want to go from the revolution
Mm.
to the curve. So what's the distance between the axis of revolution and the axis? That's 2, right? Now, is that being added or are you taking it away? It's being added, right? That's why it's +2. If the axis of revolution was above, you'd be subtracting. So again, that's why, typically speaking, it's good to have a visualization in front of you so you can easily see what's going on. Volume is then pi times the integral. We already said what the interval is going to be. 0 to 2. Right, we had to do that when we were doing the shaded part. Square of the outer radius minus square of the inner radius. $18 squared. What is it? Minus 4x squared plus 2 all squared. So 320, then minus 16x to the fourth minus 16. Oh, please say 16 is a factor of 320. That would be so nice.
It is.
What is it? What are you left with?
16 times 20.
Yeah, 10 would be 160. Oh, that makes this very nice. First term is going to be 40. Right, 20 times the length. Minus. Second term, you should see, is going to be 2 to the 5th over 5. Minus. You should see 8 over 3. Right, 2 cubed over 3. We have a common denominator of 15. Yes? 20 times the length of the interval. Length of 0 to 2. Something over 15. Oh boy.
You could just simplify like.
I could factor out.
that.
Actually, I could factor out an 8. That'll make this easier, right? 8 times 16. 64 times 2, 128. Then we're left with 5 minus 4/5 minus a third. That's gonna make this easier. Five times 15, 75. 75 minus 12, 63. 63 minus 5, 58. That's just a matter of 58 times 128. Without me pulling up a calculator because I'm stubborn. 58 times 100 is 580. $58 times 20. 50 times 20 is 100. 8 times 20 would be 160, so 260. And then 58 times 8. 50 times 8 would be... No, something's wrong. That's not 260. 50 times 20.
I got 7,424. I think that's right.
Now you just threw me off.
Well, I mean, what you could
I
do.
want 58 times 20. 50 times 20 is 1,000. And then it is plus the 8 times 20, which is 160. So that should be 1160.
You could break it off like 128 times 50, and then you can do 128 divided by 2 times 10 to get that.
Yeah,
Which
I
is
like
like that's some crunch,
I'm
right?
just doing it this way.
But then I think that's faster that way.
Then 8 times 58. I know 8 times 50 is 400. 8 times 8 is 64. This is not going to get me what I want, is it? Okay, I give up. Yeah, it should be 5,800. Okay, I can't do math. Now it's going to get me what I want. For 12. Zone 424. Again, back in the days of not being allowed to use a calculator. And then you just go like this. And you say, obviously 58 times 128 is 7,424. And that is our volume. We have a bit of time.
You're not gonna simplify that.
I'll take away 15 minutes for the quiz. So I actually have like 15 minutes left. Questions on these? See if I can quickly find an interesting problem from the textbook.
Same process of, it was rotating about the Y, but the line's off the y-axis, but it's like the problem.
The idea would be the same, right? Because the radius is always measured from the axis of revolution to.
There are totally different ways of stating about a slope line.
Yes, you want to be able to use either of these methods. Right, disk and shell strictly for horizontal or vertical, not some slope, right? Not some sloped line. I don't actually know if that's ever covered in the calculus sequence. I don't remember ever covering it, but yes, you can get surfaces that way, right?
So how would you do it?
I have no idea because I never studied it. Probably some weird fancy math in there. Probably have to rotate it or something. That'd be my guess. So that's something that Aiden can look up. Maybe make it as a extra project for him. I don't have to teach a class about it. And then I'll put it on the final. I'll probably read a headline. Student body found in dumpster. Oh, yes. Because of course we have to have trig. Hmm. So the region is bounded by y equals sine x, y equals cosine x, and x equals 0. It's being rotated about the x-axis. And we're going to find the volume of the resulting solid. Minus. Yeah, we'll just do 0 to 2 pi. This time, so we're looking for this region, right? Where do they intersect? Pi over 4. color.
Explain what this website is. Don't these colors already exist, or are they just adding names to them instead, like we did tonight?
No idea, but it gives me the RGB code of colors, so. I'm stuck between fired brick and grandma's perfume.
Fires are, yeah.
By the way, I found that website purely by chance. I was just Googling RGB codes, and that was one of the websites that popped in and said, "Oh, look at all the list of colors." Perfect. And I just saved it. Okay, so we want to set up the integral first, right? So volume pi times the integral. What are the limits of integration? The square of the outer radius. What's our outer radius? Minus the square of the inner radius. Which is what? And now we have to evaluate that. Without a calculator. Without a table. Okay. You're overcomplicating it. Cosine squared minus sine squared is cosine of 2x. Ah, now this is really easy. You may want to put to heart the trig identities. Makes your life so much easier. Sine of pi over 2. Oh dear. 1. Sine of 0. Our volume? Pi over 2. Is there another interesting one? That one's kind of interesting, but I think that would take me too long. Yeah. Any questions on disk method?
What are we rotating this region like with respect to?
Oh, shit, I didn't write that down. It's being rotated about the x-axis.